we are going to continue the remaining topics of the chapter 6, which includes the SOC architecture and MIPS processor. Before this, we have studied the two different architecture, that was VLIW, that was very long instruction word architecture, and the second one was DSP, that was digital signal processor architecture. In this type, we had studied the three types of architectures. The first is SOC architecture. If we talk about SOC architecture, it is named as a system on a chip which combines the required electronic circuits of the various computers components into a single IC or integrated chip. So what is the SOC basically? Which combines the required electric circuits of the various computer components on a single IC. So SOC is a complete electronic substrate system that can contain the analog, digital, or mixed signal, or the RF, which means radio frequency functions. What are the main components? Its components usually include a GPU, that stands for graphical processing unit, and a CPU, that stands for central processing unit, that can be multi-core, and system memory, which means RAM, that is random access memory. Because the SOC includes both the hardware and the software, it uses less power. It means there is a less power consumption, which provides the better performance and reduces to the required space and increases the reliability than the multi-chip systems. In the most systems on the chips today that come inside the mobile devices like the smartphone and tablets, an SOC is especially designed to meet out the standards of incorporating the required electronic circuits of numerous computer components on a single IC. So, this is what actually SOC means, meeting all the standards on the number of computer components by replacing it with a single integrated chip. If we talk about the further procedures of SOC, the system that assembles several chips and the components on a circuit board, the SOC fabricates all the necessary circuits into the one unit. The challenges of an SOC include higher prototyping and architecture costs, more complex debugging, and lower IC yields. Yet, we can say that IC is not cost effective and it takes time to manufacture, but it is likely to change as the technology continues to be developed and employed. An SOC usually contains the various components such as operating system, utility software applications, the voltage regulators, and power management circuits. One more, if you consider, then it can be said as the timing sources such as the phase lock loop control systems or oscillators, or a microprocessor, microcontroller, or a digital signal processor that we studied in the last lecture, with the peripherals such as the real-time clocks, counter timers which can be implemented or decremented as per the needs of the instructions, and power on reset generators. The external interfaces such as USB, Firewire, Ethernet, Universal Asynchronous Receiver Transmitter, or the Serial Peripheral Interference Bus. The remaining four we can see, that is analog interfaces such as digital to analog converter and analog to digital converters. So it is including both the types of the converters, either they may be from analog to digital or digital to analog. If we move to the RAM and ROM memory, it can be also up to the mark. If we talk about the basic SOC model, what does it define? It simply defines the interconnects that lies between the media processor and memory, or the core processor and analog and custom circuitry, and the vector coprocessor and system components. So this is the basic SOC architecture if we talk about, in which there are three upper lines and three lower lines connected with the medium line, that is called as interconnects. So the data in the bidirectional mode is connected towards the media processor and memory with the help of interconnects. Similarly, the core processor and analog and custom circuitry are connected in a bidirectional mode with the interconnects. Then the core processor and the vector coprocessor are also connected in a bidirectional mode, and the vector coprocessor and system components are connected but not in a direct mode with the help of interconnects only that provides the further transmission of data. So this was about the SOC architecture. Now if we move about the MIPS processor and programming, we can study what does it stands for. It stands for million instructions per second that defines the MIPS. It is a method of measuring the raw speed of a computer's processor. Since the MIPS measurement doesn't take into account the other factors such as the computer's input-output speed or the processor architecture, it is not always a fair way that we can ask to measure the performance of a computer. For example, we can consider a computer that is rated at 100 MIPS that can be able to compute the certain functions that is faster than the other computer that is rated at 120 MIPS. So it is almost 9 times, 8 times up to that mark. If we talk about the rest of measurements that has been used by the computer manufacturers like IBM to measure the cost of computing, the value of computer is determined in the MIPS per dollar. Interestingly, we can also say that the value of computers in MIPS per dollar has steadily doubled on an annual basis for the last couple of decades. If we talk about the code formats of MIPS, we can say on the some processors, particularly on the CISC, which standard for complex instruction set of computing, the size of an instruction code that varies within the instruction and its operands, the MIPS processor, like many RISC processors, which stand for reduced instruction set of computing processors that uses a fixed length of instructions code, and the all MIPS instruction codes are exactly 32 bits, in which the fixed length instruction codes that offer the advantage of simple instruction fetching, which means a smaller, cheaper, and processor. The smaller can mean faster, but the distance electricity has to travel determine that how long the operation will take. It also means the less power consumption and the lowest manufacturing cost. So this is about the architecture of MIPS, and while we move to the register instruction format, to the opcode source 1, source 2, destination, shift amount and functions, if we take some values, the zeros in the LSB or leftmost 6 bits that indicates to the control unit that this is a register instruction, then it uses to the rightmost 6 bits to distinguish the operation codes. And we also need to remember that the operands are not necessarily in the same order in assembly language and machine language. So this was about the MIPS instruction that we studied. Thank you.